Welcome to a new season of our deep learning web series, Comprehensive and Intuitive Introduction to Deep Learning. In season 3, we will explore the most consequential technology of our times, large language models, and the neural network architecture that powers them called transformers. What I plan to do in season 3 is to go both deep as well as broad in the area of large language models. I plan to do about 8 episodes in season 3. So this is the agenda for the entire season 3. And I will start off with explaining what the transformer architecture is. I'll not just tell you how a transformer architecture is designed, but I'll also go into the details of why certain components are attached to each other in a certain way and the intuition behind how they work. Then we'll get into the actual use cases for the transformer architecture, and we'll explore that in three different ways. One is the encoder-only transformer, the next one is a decoder-only transformer, and the third one is the encoder-decoder transformer, where I'll explain not just how they are trained, how they are fine-tuned, but we'll actually build real working use cases and demonstrations of those use cases. And we'll be able to see what they do and what the benefits are. And then we'll get into the other advanced areas of large language models, where we will explore how do you optimize an LLM both for speed and performance, and how do you improve the quality of a large language model. And one of the things is large language models are changing very rapidly. It really doesn't make any sense to just talk about the classical large language models, but it's also important to capture what are the recent advances that have happened in this space. What are the things that DeepSeek has brought in? What are the new innovations that are happening in reasoning models and so on? So we will explore a lot of those things. And again, just with everything else in the CIDL web series, I will be focusing not just on theory, I'll be focusing on the intuition behind how things work, and I'll also be focusing on the practical applications of the concepts that we will learn. So just as a quick overview of the concepts we'll be learning in season 3, I show it to you on the right hand side here. There are a lot of topics, from transformer architecture to the recent breakthroughs in terms of a mixture of experts or multi-head latent attention and speculative decoding. And we'll also get into multi-turn chain of thought reasoning. We will get into reinforcement learning and the different types of policy optimization algorithms that have made reasoning possible. So we'll explore a lot. So before all of that, I think it's important for us to get a historical perspective of large language models. We all know that LLMs are revolutionary. We all know that they appear like magic. But what are the fundamental things that have happened that have essentially led us to this moment? And it's important to understand that to see how the technology has progressed. So the way I look at it is where we stand today in 2025. The groundbreaking work for that was done in a span of 10 years between 2013 and 2023. So the first innovation that led to this moment happened in 2013. It's basically the invention of this technique called word to vec, which we explored in season 2, episode 2, which allowed text information to be encoded in a numeric format. And that numeric format carried with it certain attributes that describe each of those words. And there are different techniques that were proposed by this word to vec paper. It happened in 2013. Things like CBOW or skipgram. Again, we explored this in season 2, episode 2. But this was a very important innovation that essentially led to the large language model innovation that have happened after that. So after that came this seminal paper by Ilya Sutskever, which is basically a seek-to-seek model or a sequence-to-sequence model, where he showed how you can attach two different neural networks to translate text from one language to another language. And that gave birth to the idea of the attention mechanism that was proposed in late 2014 by Bandau and then further optimized in 2015 by Luang. And we explored this also in season 2. Remember that Ilya Sutskever's sequence-to-sequence model was two different neural networks converting text from one language to the other, the source language to the target language. The attention mechanism invented in 2015 showed how you can make certain words in the target language focus on the relevant words in the source language so that your translation quality is very good. Now, building on this is the paper, the seminal paper of the large language models called Attention is All You Need, was published in 2017 by Vaswani and team at Google. And this is the seminal paper that introduced this new type of a neural network architecture called transformers that gave birth to large language models. So 2017 was when this paper was published. In 2018 was the first implementation of two types of large language models that came out from the ideas proposed in the Attention is All You Need paper. The first class of language model is the GPT class of models, where you can train this transformer architecture so that you can start to predict the next token, which allows us to generate answers to questions that are being asked. Okay. The second class of language models that were developed is called BERT, and they were not designed to generate text, but they were designed so that you could do very high quality and very fast classification of text and do other things like named entity recognition and extractive summarization and so on. So that was the seminal work that showed that you could take a transformer architecture and with high performance and high quality, you could build language models with it. And 2021 is where OpenAI basically took this idea and they showed that you can not just generate human text, but you could generate code using the large language model ideas that are proposed in GPT-1 and the transformer architecture that was proposed in Attention is All You Need paper. Then came in 2022 the another seminal paper called Instruct GPT, which is where the idea of reinforcement learning was introduced so that you can fine tune the large language model so that it is mimicking the human preferences when it's spitting out answers. Now, phase or this era of between 2013 and 2022 is what I call the foundational research era. So this is the era in which you had a lot of innovations that were made that enabled this movement of large language models to be commercialized going forward from that point. So in 2022, November is when GPT-3 was released to the world, and that started off this whole revolution where the end consumers were able to appreciate this technology shift that had happened in deep learning, and it was actually magical. The first users, when we all used GPT-3 for the very first time, we saw it as magic because earlier you could search for information, and what you would get in the search experience is you would ask a question and the search engine would recommend you sites where you would find the answers. What GPT-3 showed us is that you don't really have to go anywhere. This algorithm will actually show you the answer to the question you're asking. So it looked like magic. And of course, our CIDL web series is to understand how this magic is actually performed so that we can repeat this magic in solving newer problems. Anyway, so GPT-3 was published to the world in 2022. Then came a series of other large language models that basically competed with GPT-3. Of course, Google released Gemini, and then you had Mistral, then you had Claude, and you had Llama from Meta. And these 2 years is where I call as the commercialization era. And this is the era in which you would see large language models gain mass consumption. In fact, there was this very interesting statistics that was published saying that if you look at all the technology transformations that have happened in our industry, right from the invention of electricity till the large language models, electricity took several decades for hitting the first 100 million users. Even internet, which happened in the late 90s, mid to late 90s, that took, I think, in the order of about 11 years or something to hit their first 100 million users. But large language model, ChatGPT, for example, hit their first 100 million users in just 60 days. It has never happened in history that a technology shift has gained that fast a commercial adoption. So, yeah, this era of between 2013 and 2023 is the magical era, this 10-year period is the one that gave birth to this massive shift that we are seeing in the industry today called generative AI. And then, of course, 2024, DeepSeek published their seminal paper that showed that you don't just throw more hardware at the problem. There is a lot of algorithmic simplicity and elegance that you can bring in to improve the performance, speed, quality, and bring down the cost of both training and inferring from these large language models. We will explore these ideas that DeepSeek proposed in as part of season 3. And now we have entered this era in 2025 where we are just gone past just next token prediction. We have gone into what we call as reasoning models, which is also something that we'll explore in season 3. Now, if you overlay this period between 2013 and 2025 to capture the economic value that was created by this shift in technology for these 4 publicly traded companies that are gaining the most from this AI shift, NVIDIA, Microsoft, Google, and TSMC, you see that we really do not have any company in the trillion-dollar market cap range. And if you look at it in 2022 onwards, when GPT started to take off, you actually see that these companies' valuation shot up from being in the higher order billions to trillion range. And this is the economic value that was unleashed by this new technology. Now, this is, of course, in the public space, but even in the private space, among the companies that were AI first, you actually see that the valuation of these companies, whether it's OpenAI, Anthropic's, Perplexity, Cursor, Hugging Face, and so on, they went from their seed round funding of hundreds of millions of dollars and going through billions of dollars of valuation. And just look at the value that was created just between their seed round in 2025. You're talking about 400 plus billion dollars of valuation that was created just by these companies alone. And just look at the growth, the valuation growth from the seed round to 2025. It's unheard of valuation spike. Of course, valuation can be frothy when it comes to these private companies in the hot space. But even if you look at revenue, we are actually seeing record revenues being generated by these companies. In fact, we are seeing $100 million of ARR being created in just less than 2 years, which is also something that has not been heard of in the industry so far. So again, not just the technology shift, but there's a lot of gain that we're seeing from the value that's created economically. Now, we will start our season 3 with this paper here. Attention is all you need. The seminal paper, as I said, that transformed the industry. All right. So let's explore the ideas that are published in this paper. So attention is all you need is a paper published by 8 Google researchers in 2017. So it ranks among the top 10 cited scientific papers in all areas of science in the 21st century. It's the second most cited paper in computer science, and it is also the fastest growing citation trajectory among all the AI papers that are published. And in this paper, these authors propose this new form of a neural network architecture called the transformer neural network architecture, which is shown in this picture here. All right. So before we get into understanding what the transformer architecture is, maybe it's important to just zoom out a little bit and get an understanding of the different nomenclature that is thrown around. Things like transformers, large language models, small language models, RAG, and agents. So let's just get a concept map to understand how these things are related to each other. So at the base of everything is the transformer neural network, just like we studied feed-forward neural networks in season 1 and recurrent neural networks in LSTMs in season 2. This is a new form of a neural network architecture called transformer neural network architecture. Now, the transformer neural network architecture is a foundation for what will become a large language model. So the neural network weights in the transformer, when trained and fine-tuned for specific languages or specific use cases, becomes what is called as a large language model. Now, it is usually large language models they have billions, and in fact, the latest large language model also has trillions of weight parameters. So that's why it's called large. But sometimes you really don't need that big of a language model, especially if you're just focused on one area. You really don't need to have a large language model that is trained on entire on languages and on physics and biology and chemistry and so on. We just want to focus on one area. So you can actually train it to be a small language model. Either you train it by decreasing the number of parameters or doing a few other things that we'll explore in this season. Or you take a large language model and you distill it down, so you create a small language model. So an SLM is a language model, but it has much fewer number of parameters. So it can actually run it on edge devices, on your laptop and so on. Now, one way to further fine-tune a large language model to align its responses to human preferences, you use this technique called reinforcement learning. We'll explore that also in season 3. And then we hear this word agents a lot in 2025. So agents, the very easy way to understand this is to look at it as a workflow engine that connects one or more LLMs as well as one or more other services that it can interact with to complete a task that would take multiple interactions with either a large language model or multiple SaaS services. That's what an agent is. And an agent can also rely on a concept called RAG, and that allows you to bring in your organization's data so that you can blend in search along with the generation capabilities of a large language model, which is also something that we'll explore in season 3. So this is how all of these different concepts are interconnected. Okay, now let's get in and let's start with understanding the transformer architecture. So in this episode, episode 1, what I will do is I'll focus on giving you the most intuitive understanding of the transformer architecture. And you'll also not just understand how these different components are connected in a certain way, you'll also understand why they are connected in a certain way and what is it that they accomplish at the end. Okay. Let's start with the architecture that was proposed in the paper, which is this one here. So this transformer model that you see here that is proposed in the paper is actually 3 different models. So the first model is what we call as an encoder-only model. And this encoder-only model by the way, is just this part of the transformer. By the way, you see that I've actually redrawn the picture. So this picture that you see on the left is what is there in the paper as it is. I've actually redrawn it so that the bottom layer, the input layer, is more cleanly laid out in my diagram, but it's the same thing. So the first model here is what is called as an encoder-only model. The second model is what is called as a decoder-only model, and that focuses on a subset of this part of the architecture that is proposed in the paper. Not the whole thing, but a subset of it. And the third model is a combination of both of these things, which you see as a full picture that is there in the paper, which is called as the encoder-decoder model. So you have the encoder part, and you also have a modified version of the decoder, which are then connected together in this way. And that forms the encoder-decoder model. Okay, now let's just double click and try to understand what are these three different models and why do you need three. So the first one is the encoder-only transformer. So this is a much more simpler way of explaining this. So you feed in the text into the encoder-only model, and you have one or more encoders that will take the text and they will produce what is called as a contextual understanding of the text that is fed in. So why would you use something like this? You would use something like this not to generate text. That's the key thing to understand. Encoder-only models do not generate text like a GPT model does. What they do is that they allow you to classify text. For example, you can figure out the sentiment that is conveyed by a tweet or a movie review or something like that. Or you could use it to label data saying that, hey, what this particular news article has topics relevant to politics or sports or technology and things like that. You can do spam detection. You can also do this thing called named entity recognition, where you give it a text and it will extract very quickly things like their names in the text. It'll extract that, phone numbers, if they are places or countries or addresses or dates or IP addresses or social security numbers, whatever it is, it'll be able to extract that just by looking at in a block of text. It can also be used to do similarity searches. For example, when you go to Quora or Stack Overflow, you ask it a question and then it'll say, okay, these are the other questions that people are asking, which are similar to the question you're asking. So that's very useful. I mean, and the encoder-only transformer will allow us to do those things. It also is used for what is called as extractive summarization or extractive question and answering, where it will not generate an answer for you like a GPT would, but given multiple choices, it's a model that can be trained to pick the right choice from a multiple choice question and answering prompt. So there are different models in this class. The classic one is called BERT, and there are several variants to BERT called Robert, Albert, Testel BERT. There is another form of encoder-only transformer called Electra. By the way, we'll go into the details of an encoder-only transformer in episode 2 of season 3, where I'll tell you how you train it, how you fine tune it, and then how you solve real life problems using an encoder only transformer. So this is the first model that is there in the transformer architecture. The second model, as I said, is called the decoder only transformer. So the decoder only transformer is the one that when you give it a prompt, it will generate tokens, and that tokens essentially form the answer to the question you're asking in the prompt. So this would be like what you see with the large language models that usually all of us relate to, things like GPT or Gemini or Claude or DeepSeek or Perplexity or Grok or what have you. And there's a lot of open source variants also like Llama, Mistral, DeepSeek, and so on. So this is useful for generating text, either answering questions, writing code, writing articles, summarizing articles, and so on. And the third form of a transformer architecture is, as I said, where you can attach the encoder and a variant of the decoder so that you can take text from one language and convert it into text into a different language. It can be human language to another human language. Like, for example, you give it an English sentence and it can convert it into Hindi or French or Telugu or whatever other human language, and vice versa. Or you can give it, let's say, human language, and then it will generate machine, readable text like the source code. Or, for example, you can express what you want in English, which is human language, and into the encoder, and the decoder will spit out, for example, the Python code relevant to the question or the prompt that you're giving in English, or it can spit out the SQL code and so on. So human languages to machine language translations also can be done with the third form of a transformer called encoder decoder. Okay, so we will study all these three different models in season 3 across the multiple episodes. Okay, so with this out of the way, let's now get an understanding of the individual building blocks that form the transformer. To understand all three types of transformers, we just have to understand 13 concepts, which I show here. And also show you a table that tells you which of these concepts applies to which of these transformers. Now, this 13 is quite a bit to capture in one episode. So what I will do is I want to show you a subset of that, but I'll show the subset in such a way that you feel that you have completeness. You essentially have an understanding of at least one of the models. And so we'll focus on the encoder-only transformer because the components that are there in the encoder-only transformer, which are 9 components, apply to all 3 transformers. So I think this is a good starting point for us to actually start understanding the individual building blocks of the transformer architecture. Okay, let's dive in now. So let's start with the very first out of the 9, the very first concept, which is word embeddings, which you see here. So let's start from the bottom and go up. So you see the text goes into the transformer, it gets tokenized. Neural networks do not understand text, so you have to convert it into numbers. So the first thing you do is you use word embeddings to get the embeddings matrix for the text. Okay, we studied this in season 2, episode 2 exhaustively. I showed you different types of techniques like continuous bag of words, skipgram, glove, and so on. And I showed you that what you do with word embeddings is you take text and you run it through these algorithms. And what these algorithms do is that it will extract the different features. What you do is that you say, these are the number of features that I want. They're also called dimensions, by the way, feature dimensions. Right? I mean, you cannot say this is the type of feature I want you to extract. You cannot say, for example, I want you to extract a fruit and a name and place. You just say that, okay, I'm going to give you text. You're going to process all the text. You can figure out how these texts are connected to each other and just give me back a vector for each of the words, the unique words that you see in that text. And for each of those words, that vector is going to have a dimension of d, which is the number of features that you have extracted. And those features could be anything. Depending on the type of text that you send it, it's going to extract those features that show the connectivity between all the words and the sentences in that text. Okay. For example, you give it some text and let's say it extracts features like, is it a fruit? Does it have taste? Is the word describing the name of a company? Is it the name of a person or a company or an organization? Is it a place? Is it a thing? And so on. And then it's going to give it some values. And one of the beauties of something like this is now that you have something like this, you can use math to figure out what words are related to each other, what words are unrelated to each other, what words are opposite to each other. And the way you do that is, let's say that you just have 3 dimensions. I just show 3 dimensions because as humans, we can only see something in 3 dimensions. Now you take 3 dimensions only, and then you go to plot, let's say the words Apple, Orange, Laptop, Microsoft, Book, and Google on a 3-dimensional graph. And let's say this dimension is company, that dimension is fruit, and this dimension is object. And depending on the values that you get out of this word embedding technique, right? What you'll see is that similar words will start to cluster together. Like Microsoft and Google, you see that they're clustered together. Apple and Orange are clustered together. Laptop and book are clustered together. And you also see that those things that are dissimilar also tend to start to move away from each other. So this is beautiful because now we just don't have random numbers that describe text, but you actually have a vector and individual elements in that vector carry the different features that express what this word is about. Okay, so that's word embeddings. Again, as I said, if you want to dig deeper, go back and look at the recording of season 2, episode 2. And I show you not just how they are built, I show a lot of things that you could do with it. Very interesting, fun experiments that you could conduct with word embedding. So anyway, so the first block here is the word embedding. So now let's see what would happen when you pass in a text into this stage of the transformer. So let's say the text is, I walked into Apple store eating an apple. This is text. You pass it through a tokenizer. The tokenizer will tokenize it using a variety of different tokenization techniques, which we studied in episode 1 of season 2. Like byte pair encoding and so on, word piece encoding or whatever it is. So let's say it tokenizes it on the word boundaries and it becomes I becomes one token, walk becomes another token, into becomes another token, and so on. The tokenizer typically also adds some padding. And again, this is something that I explained in episode 3 of season 2. The idea behind padding is that you really want to have a fixed size input to a neural network because whatever you give to the neural network, it designs the input neuron, number of input neurons based on the input length. And text has variable length. Each sentence could be of variable length. So how do you make sure that every text that you feed in has the same length so that the neural network can be designed to have a fixed number of neurons at the input layer? You do that by first determining what is the maximum size of input that you would like to feed in. And if a text comes in and it is less than that maximum, then what the tokenizer will do is that it will add these special tokens called pad tokens, which have an embedding value of zeros, all zeros, right? If you give it as an input sentence that is longer than the maximum thing that you designed this for, then it's going to truncate it. Okay. So anyway, so what we have done here is that you pass it through a tokenizer, it tokenizes it, and it adds these padding tokens as well. By the way, you hear this word called context in the large language model world. Context essentially and context length and things like that. You see here things like, hey, what GPT-2, GPT-3 has, I think, a 4K or 4,000 word token context length, and the latest version of Llama 4, I think they're saying they can actually do 1,000,000 tokens in the context window. What it essentially means is they have designed their transformer in such a way that at any given point in time, they can actually see so many words, right? Obviously, you're not going to have, let's say, 4,000 words in a single sentence. You can essentially pack it with multiple sentences, but the total number of words that are there in all those sentences put together is what is the context length. So they size it, let's say, for 4,000, which means that you can feed it any number of sentences and it will keep packing it till it hits about maximum of 4,000 if the context length is 4,000. That's all it means. Okay. So you're passing the text, it has tokenized it. Now what you do is that you get the embeddings for each of these tokens and you build this embedding matrix. So this matrix is sized S cross D. S is the sequence length. So here, how many sequences I have determined that my transformer is going to have no more than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the maximum number of tokens that I'm going to allow into my transformer. Again, this is a toy example, but this is illustrated so that you can actually draw those pictures. That's why I just picked 10. Typically, you would pick more than 1,000, whatever. If you're designing a new transformer, then you can choose whatever value you want. Okay. In the case of the GPT-3, it was, I believe, 4,000. Okay. So the first S is a sequence length, which is the total number of tokens that you're going to allow into this. And they will form the number of rows that you see in this matrix. And the columns are the number of feature dimensions that you have captured as part of your word embedding. Like in the prior examples, I showed you fruit or name or company and all that. Each one is a dimension. So you would show that I'm showing that as D here. How many features are there? D number of features. So they become the columns. So each vector, for example, here I on dimension 1 is 0.37, dimension 2 is 0.95, and dimension D is 0.59. Okay, if you look at Apple here, 0.83, 0.21, and whatever till 0.18, Apple appears twice to capture the same embedding in the word embedding, which is this part of the transformer, right? So what you get in this step is take input, tokenize it, and you build this matrix, which is matrix sized S cross D. Okay. All right. Now let's go and look at the next part of the transformer, which is what is called as positional encoding. Now, positional encoding is the first breakthrough idea of the transformer architecture. So let's spend some time trying to understand what this is. Now, what we know is that text or language, the order in which words appear matters. I mean, just look at these sentences. Even though she did not win the award, she was satisfied. Versus, even though she did win the award, she was not satisfied. All I did is I took the word not and moved its position from somewhere in the middle to somewhere in the end. And the meaning of the sentence is completely changed. All the words remain the same, just the position of what the word has changed and the meaning completely changes. Or she alone finished the task is not the same as she finished the task alone. Again, here I've just changed the location or the position of the word alone and it completely changes the meaning of the word. Or snake bites man, and if we just flip the wordings and say man bites snake, they're not the same thing. So the position of where a word appears in a sentence or in a block of text is very important to understand its meaning. Right now, the whole idea behind positional encoding is how do you give this position information to the transformer? Right, you already are giving the word embedding information. How do you give the positional information to the transformer? So let's think through, reason through this thing ourselves before we see what was proposed in the paper. But before we go there, what was the way in which this was done prior to the transformer? Prior to the transformer, I showed you recurrent neural networks and its variant LSTM networks, where you could give a text and it would process the text. And the way they would do that is they would take the text, let's say the text is the cat sat on a mat, they would tokenize it, and you have 1, 2, 3, 4, 5, 6 tokens. And what they would do is that in a loop, right, in a loop, they would go and process one token, build some state, and then they will go on to the next token, compute again the modification to that state, then go on to the next token, compute a modification to the state that was modified when they looked at cat, and so on, keep on going, token by token by token. So there are n tokens. They make n independent calculations, and each of those calculations allows an RNN or an LSTM to build the context that is flowing across all these words so that it can understand the meaning that is conveyed by that sentence. Okay. So prior to the transformer, you would use a loop to process one word at a time, and you would make, let's say there are n tokens in input text, it would make n independent calculations. So nothing is parallel, everything is independent. So think about it this way. Let's say that you're trying to build a neural network to understand a Wikipedia article. And a Wikipedia article typically has between 1,000 and 2,000 words, which means that if you want to build a neural network architecture using an RNN or an LSTM, you would make 1,000 or 2,000 independent calculation word by word, which is tremendously slow. And it's going to be a problem if you want to give it very large context windows. And large language models, as we see them today, through, like, say, through ChatGPT or Gemini or Grok or Perplexity or what have you, nobody would like it if you give it a question and it takes, let's say, 20 minutes to answer your question. You want almost near instantaneous responses, right? For that, you need to figure out a way in which you can process all the tokens in one shot in parallel, which is also great because then you can leverage the parallelizing benefits that are available through GPUs. So this is how we would make the neural network pre-transformers understand the ordering of words in a sentence. Now, we have to now figure out how to parallelize this so that you don't do one word at a time and you look at everything in one shot. So let's build this out. Okay. Before we see what was proposed in the paper, I think it's important for us to build out the intuition behind how they arrived at this technique. So what are the properties that positional encoding should have? Number one, it should be a matrix. Why should it be a matrix? Because you have this matrix here, which is the word embedding matrix, and it describes each of the input text in numeric format. You want to now add to it the location information also, so that the order in which these words appear. Correct? Now, obviously, you also want to make the size of this matrix where you're encoding the position to be the same as the size of the embedding matrix. So the embedding matrix is S cross D. S is the number of tokens that you allow at the sequence length here, and D is the number of dimensions. You also want to have the positional encoding matrix to be the same size. So this is our requirement. Okay. Now, how do you fill this requirement? So one obvious idea is, okay, why don't I just give it absolute numbers? Okay. So I is at token position 0. Walked is at token position 1, into is at token position 2, and so on. So why don't I just use that? So I fill up each first row with 0, 0, 0, 1 with position 1 at 1, 1, 1, position 2 at 2, 2, 2, and so on. Why don't I do that? So the problem with doing something like that is, as the number of words increases, its position value increases. And at the end of the day, I'm adding up these two vectors. When you add up these two vectors, does it mean that words that appear towards the end, which have larger position values, do they signify more meaning than the words that appear at the beginning? Absolutely not. Correct? So just using pure math to assign absolute position locations will not work at all. Right? Okay, so that does not work. What do we do? Okay, how about we do this? Why don't we divide the absolute position number with the maximum sequence size? So I take the absolute position, which is 0, 1, 2, 3, and divide it by the total number of tokens in that sentence. So I'll get smaller numbers, but still, it still doesn't solve that problem, because the words that appear towards the end will still have a bigger number. Yes, they are smaller in magnitude, but they're still bigger, relatively speaking, than the words that appear at the beginning. So this is also not going to work. All right. It is not going to work. How about the following? Why don't we actually encode the position information in binary? Okay. So for example, I walked into the Apple store eating an apple. Position 0, so on. Encode this in binary. So 0, 0, 0, 0 is for position 0. 0, 0, 0, 1 is the binary representation of 1. 0, 0, 1, 0 is for 2, and so on. So I represent it this way. Now, one way this is good, because machine learning and deep learning algorithms are in love with zeros and ones. So perfect. You don't have really big numbers. You have a matrix, and either the number is 0 or 1. Perfect, right? Actually, no. Because the problem with something like this is, let's say that I increase the sentence length, right? I walked into Apple store eating an apple, glancing at the sleek displays, noticing the new iPhones lined up neatly, while a kid played with an iPad and a couple debated which MacBook to buy for college. If I were to take something like this will be a much larger sized sequence. And if you fix the number of dimensions here, let's say I'm showing 4 dimensions, right? When you hit the 17th token, you don't have space in this. So if you don't have space in this, what it means that you actually have to expand the number of dimensions in the positional encoding matrix, which will not work, because you're going to add this positional encoding matrix to the word embedding matrix, which is dimensioned as S cross D. So as the sentence length increases, your binary format really does not help you either. So all strategies so far that we have explored do not work. The absolute numbers do not work. The relative numbers or normalized numbers do not work. The binary representation does not work. So what really works? So the authors of Attention is All You Need proposed a very interesting technique that you could use to build this positional encoding matrix. It's basically described in just a very small paragraph in the paper on page 6. So what they say is, okay, your goal is to create an S cross D matrix so that its size the same as the word embedding matrix. So for each of these columns, for a given word at some position, let's say position 0, this word, which is I, for each of these dimensions, what you do is that if the dimension is even, right, then the formula that you would use to fill in that value is sine of the position of that token. Let's say you're filling for 0. So 0 divided by 10,000 raised to the power 2 times I. I is the position of the dimension, which is, let's say, 0 here, right? 2 times I divided D. D is the total number of dimensions. So let's assume that you had 7 dimensions as an example, okay? So what you would do is that for the very first slot here, what is the first word? This is position 0. Try to fill the first slot here, which is dimension 0, which is what? Even? Yeah. So sine of position is, for this word is 0, divided by 10,000 raised to 2 times position of the dimension is 0. So 2 is 0 divided by D, which is 7 is what he said, the total number of dimensions. Okay, now let's get to the next one here. So same word. So what is the position of this word? It's still 0, same word, correct? And this dimension is 1. Okay, let's say you're doing 0-based indexing, so this position is 1. So is that even or odd? It is odd. So if you do odd, you say cos of, what is the position of the word? It's still 0, 0 divided by 10,000 raised to 2 times. What is the position of the dimension? Is 1, if which is odd. So 2 times 1 divided by total number of dimensions, which is 7. When you get to the next slot, it is dimension 2, which is even. So you do sine of position, which is still 0, divided by 10,000, 2 times 2 divided by 7. Get to the next one, 3, which is odd. Cos of position still 0, 0 divided by 10,000, 2 times 3 divided by 7, and so on till you fill out all these column values. Then you get to the next position, which is the next word, which is at position 1, and you do the same thing. So this is what they proposed. But how? I mean, how did they come up with something like this? The goal of CIDL web series is not just take anything at face value. We would really want to understand the intuition behind how might they have come up with such a interesting and a non-intuitive idea. While they don't explain it in the paper, the way I think that they might have come up with something like this is if you go back to our binary representation again, and I'm actually going to take a much longer string here, which is that I walked into Apple store eating an apple, glancing at the sleek displays, noticing the new iPhones lined up neatly while a kid played, and so on. So it's basically a lot of words, about 38 tokens and so on, 38 words. And let's say I have, these are the number of bits that represent this, okay? 000 for position 1, position 0, and 00001 for position 1, 00010 for position 2, and on. So you understand this. Now, if I were to color code this at the first one here, right? And I alternate. So all the zeros I mark it as green. 0 is green here, and so on. And all the ones I mark with yellow. So you see that 0 and 1 are alternating color-wise. I'm using color as a way to represent a pattern here, okay? You see 0, all the, let's say, even numbers or even things are colored green and odd are colored yellow. Now we get to the next dimension here, and if I were to use the same coloring scheme, and I'll say all zeros should be green and all ones are yellow, what I see is that in the first column here, you'd see that 0 and the green and yellow alternate with every row. In the second column, you see that you have 2 zeros followed by 2 ones, and then 2 zeros followed by 2 ones, and so on. Then you get to the next one, you see that there are 4 zeros followed by 4 ones, 4 zeros followed by 4 ones, and so on. Get in the next one, you have 8 zeros followed by 8 ones, 8 zeros. Now we see that there's an alternating pattern here. The greens and the yellows are essentially alternating, and the frequency changes as you're going from this bit all the way from 0 to bit 5. Okay. If I were to plot this, this is how it's going to look. So you have the first one going this way, the second one going this way, the third one going this way, and so on. Essentially, the frequency changes as you're changing the index of the dimension. Okay, so as you can see, this follows a sinusoidal pattern, correct? And that, I think, is the intuition behind how they came up with this formula. But the question is, why are they doing sine and cosine, and why are they changing between sine and cosine based on whether it's even or not? I mean, they could actually have just stuck with just one of those things, either sine or cosine, because all you want is this alternating pattern. But what happens is that when you use both sine and cosine for the same position, you get essentially double the representational density, in the sense that even for the same position here, you would basically see that if you were to use cosine, the value would be like this, and you could have two distinct values for the same position but different embedding dimension index. And that is the reason why they chose sine and cosine, and they alternate between even and odd. It just doubles the representational power, and you can essentially create a pretty nice matrix out of that. Okay, and the code to actually implement this is pretty trivial. It's a few lines of code, and here I show you for this sentence: I walked into Apple store eating an apple, glancing. The big sentence, assuming that there are four dimensions. Using this algorithm, you'd essentially get something like this. Okay, and as you can see, as long as you fix on a certain number of dimensions, regardless of the length of your sentence, you would still get the same number of columns, right, in using this strategy. Now, this is what is the technique that is used to create this positional encoding matrix. Now, the benefit of something like this is now you can basically, because it's the same size as your word embedding matrix, you could add it up and you would be able to construct the final embedding matrix for this incoming text, which is encoding, of course, the word embeddings, plus also the positional information of each of those words. Now, this can be massively parallelized because you're just one matrix. And when you do a matrix math, the GPUs and the CUDA kernels and all that are optimized so that they can leverage the parallelism that the GPU cores offer. And then you would be able to process very large texts in parallel. You don't have to make, there are S tokens in your input string. You don't have to make S independent calculations. You're essentially doing it all in one shot and exploiting parallelism. So that's why this is one of the breakthrough ideas. It's pretty simple once you understand it, but it's a breakthrough idea that enabled large language to get models to get the speed that we see. Now you're done with the positional encoding. You add them up and you get this X, which becomes the input that you feed into your transformer, correct? And then you get this next one, which we'll call as self-attention. Okay. Now, self-attention is the second breakthrough idea of the transformer architecture. In fact, if you think about it from a breakthrough point of view, there are only two breakthrough ideas. One is a positional encoding, which gives you massive parallelism. The second is self-attention, which we'll explore shortly. And the rest of the other things are beautiful engineering optimizations that actually give you speed, performance, and quality of results and so on. But the two novel ideas are the positional encoding that gives you parallelism and self-attention. You'll see the benefit of that shortly. So this is the other one that we need to study. Now, self-attention, understanding this intuitively is very important because it is the basis on which pretty much all of large language models operate. Okay. Now, what is self-attention? So if you look at a sentence like this, actually, let's just go back a little bit here. Okay. If you go back to this picture here. In this picture, as you can see, I walked into Apple store eating an apple and pad. The word embedding for the words are different. For each word is different. But for the same word, I mean, the apple word appears twice. It carries the same word embedding, correct? I mean, it's obvious because it's the same word. But now, if you go back to this sentences here, I walked into Apple store eating an apple. Clearly, in this sentence, the first apple is actually referring to the company Apple and its store, and the second apple, while it's the same word, it refers to the fruit that's being eaten. A few more illustrative examples. Sitting on a river bank, I was thinking about my bank account. As a human, you very quickly know that the first bank here is basically representing a landmass, and the second bank is representing the financial organization, right? Or sitting on a river bank eating an apple, I checked my bank account balance using my Apple phone. And as a human, you clearly know that while the word is the same sentence, that it actually means something different based on the context in which it appears, right? But this is the key insight behind self-attention. What the authors basically said is the same word can have different meanings within the same text, basically based on where it appears and based on the surrounding words. Okay, so what it really means is while the embedding matrix, the word embedding matrix for the word is, let's say in this case, apple is the same, you actually have to change it so that you tune it in such a way that the features that represent that word in the current context actually get enhanced so that you can essentially understand that the second word refers to apple, and the features that are less relevant in the second word, the less relevant is that it's an organization, that goes down, and in this case the organization and the company feature dimension is amplified more, and the fruit and its taste or whatever it might be, that feature dimensions value is muted, right? So essentially the high level idea behind self-attention is, can we take an embedding matrix for these words and can we actually contextually modify it, is what the idea here is. Okay, that's what self-attention is. Now, instead of diving straight into the implementation, let's actually try to intuit this through this thing a little bit more. Okay, so what it means is that you basically look at each word and the different features for each of those words, and then you amplify those features for that word that would enhance its meaning, and mute those features that would actually again enhance the meaning but don't take you in a different direction in terms of its understanding, right? So in this case, for example, eating an apple a day makes a doctor go away, that as a human that you would actually enhance the fruit dimension, you want to amplify that, because in this case this apple refers to the fruit, whereas I bought an iPhone from an Apple store, as a human that you're not buying an iPhone from a fruit store. So that in this case, the word apple, you would essentially amplify the company dimension and you would suppress the fruit dimension. Right now, before we get into the implementation, I wanted to take a moment to explain what self-attention is in one sentence. Okay, so this is a sentence, and I'm going to unpack the sentence in few words at a time. So the first one is self-attention adjusts each token's embedding. So you have reached that point in the transformer where you have taken the token, the sentence, you have tokenized it, you have used the word, you have determined the word embeddings, which is the matrix called E. You have the positional encodings, which is the matrix P. You add them up, E plus P becomes this X. Okay, and that the word embeddings for the same words are the same at this stage. Apple is 0.83, 0.21 in this position as well as here. But when you add the positional information, obviously because the position information is added, it changes, but the actual base values for the word embedding still remains the same. Okay, so the goal behind self-attention is to adjust each token's embedding. So basically you take, let's say, this apple here, you want to adjust these individual cells by blending in information from all tokens in the context, including itself. So basically look at every other token that is there in this context, correct, including itself, and then you say, hey, what, in this case, this apple, right, this presence of this apple, how does it influence the embedding values of these other words too, myself as well as these other words too. I want to amplify this. For example, when I look at store, I want to amplify that this store is more focused towards an organization or a company's place where business is conducted. And if I look at this eating, I want to amplify the fact that it is an action performed on a fruit, right? And so on. So essentially you're blending in the information from all other tokens that appear in this same context, okay, including itself. That's key. Even you're changing the embedding of the word itself because you're borrowing from other things also. And we'll see that shortly, okay? The next thing is weighted by what? You weighted by how relevant they are in interpreting that token's meaning. So what it means is that you're changing all these individual cells and you change them weighted by how relevant they are for interpreting what that word actually means in that context. Again, we'll go into more detail shortly on what this means. And then what you produce is basically an enhanced context-aware embedding matrix. So the self-attention module, all it does is it takes this word embeddings plus positional encoding matrix and then it passes it through a calculator and it emits back the same size matrix S cross D, where each word's embeddings is now modified so that the other layers of the transformer now understand that, okay, in this sentence, this apple refers to more of a company and the second apple refers to more of a fruit, right? So this is original and this is the context aware embedding. Okay. Now the goal is what? The goal is you take this original, again, I'm just showing some random numbers here. This is not how the actual like the embeddings might look like. But let's say when you add up the original word embedding per positional encoding, let's say this is how it looks. Okay. I walked into Apple store eating an apple, and the dimension, there are 7 dimensions and there are 8 words, right? So it's 8 cross 7 is the size of this matrix. And I has person value for that dimension of 1 and every rest of it is 0. Walked is, yeah, person walks, so it's 0.4, and an action, yeah, walking is an action, so 0.9. You walk in a certain direction, so direction feature also is non-zero at 0.3. It's not a brand does not walk, a fruit does not walk, so it's all zeros and so on. You walk into a place, so it's 0.1 and so on, right? Now what you want to do is that you want to produce a context aware matrix so that all these values essentially are changed. Okay, right now I'm showing the same, and I'll show you how these gets changed from this to that. This is a sentence. Now you look at the first row, okay, the first word, basically I. Now what you do is that you have to figure out a formula. We'll show you shortly how to figure out that formula. What you want to figure out is what feature values will I give away. In this case, for this sentence, What I want to give away is a big chunk of the personness feature trim. I want to give it to other words. And what I want to pick up from the other words is a little bit of action. So I know that this word I is actually performing this action of walking as well as eating, right? So I want to pick up. Right now, in the original word embedding, I don't have any value for action. But in this sentence, this I is doing walking and eating as an action. So I need to borrow that from other words, right? And I also need to borrow the original one for the word I, there's no direction. I also need to borrow from the other words that I am walking in a certain direction. So I want to borrow that. I'm walking into the store, for example, right? And then the next one is you also want to borrow a brand, a little bit of value from brand, a little bit from fruit, and so on. The net effect is what? The net effect is you might have started off with all zeros for the rest of the feature dimensions and one for the person dimensions for this token I. But in this sentence, after you make this change, for the net effect you want is this word I knows that it's carrying this context to know that it is actually moving in a certain direction and it is eating something and it's moving into a certain company or a certain place, right? So that's how it's modified. Now, how you would make this modification is where the whole formula comes in, but we'll get there shortly. Let's do a few more words so that this idea becomes very clear. Let's go to the next token, which is walked, right? So you say, okay, the walked, there's a huge chunk of, for the feature dimension called action, there's a big value there because walking is an action. So I'm going to give away a big chunk of my action to the other words so that the other words know that, for example, the other word, let's say I, knows that it is walking, and the word Apple Store, those two words know that somebody's walking into it, right? And so on. So you essentially you give away some value of your action to the other words, and you pick up other feature dimensions from other words like a little bit of brand, a little bit of fruit, and all that. Because what you want to know is that the net effect is what? Walked is still a verb, so there's some action. But you also know that somebody is actually walking, they're doing that action. The word I is doing that action, and it is doing that action while directionally going into a brand called Apple. And it's also doing by also performing another action called eating simultaneously. A little bit of feature from even the fruit is also borrowed from this context. That's how you'd make that change. I keep going. In Apple, for example, actually, let's just do two more words so this idea becomes very clear. So this word Apple here, you'll say, I'm going to give a big portion of my brand away. Let's say the original one is 0.9 feature value for brand and 0.9 for fruit. Right now, it does not have anything for person, action, direction, and place and article. But let's say these are the two things. What the way you would like to modify this occurrence of the word Apple is, I want to keep a big portion of my brand because this is referencing a store, which is the store of a particular brand. So I want to keep a big portion of that. I want to give a big portion of fruit because in this context, this occurrence of the word apple is actually not referring to a fruit. So I'm going to give a big portion of that to the other words in this sequence, in this context, and all that. And I also want to pick up other things. I want to pick up that, okay, somebody is entering. So I want to pick up some portions of person from other words, some portions of action from other words, some portion of direction, and so on. So the net effect when you make this change from this to something like that is you still retain most of the brand feature value, because that's what this particular occurrence of the word apple means, and it also makes these connections with other words. Now, don't get hung up on these actual values. These are all just representative values. I mean, they might actually be something completely different when you calculate it, but this is just an example to show that this is how self-attention actually can be intuited through. Now, actually, let's go to the last occurrence of the word apple. We already seen this for the first occurrence of the word apple. Let's go to the last occurrence. In the last occurrence, when it started again, it had the word apple itself has, for the feature dimension of brand, it has 0.9, and the feature dimension of fruit also it has 0.9. Now, in this occurrence of the word apple, it's the second occurrence of the word apple. In that context, it actually means fruit, right? Because it says eating an apple. It's not a store. So what you want to do is that you want to keep a big portion of the fruit. You want to give away most of your signal of brand, because this particular occurrence of the word apple does not mean brand. You're not entering that store of that brand. But you also want to pick up a little bit of action because somebody is eating it. So you want to pick that up. You want to pick up a little bit of the person feature from other words. I is eating it, so and so on. So the net effect of something like this is you're essentially keeping most of the signal of fruit, giving away most of your signal of brand to the other words, and pulling in other feature values from the other things. So now what you've done is that you've started off with an original embedding matrix like this. And now you've converted that into a context-aware matrix like this. Now, when you look at something like this, I can say that, okay, each of these words have now blended in the feature values of the other words so that I actually now contextually know what's really happening here. Now, the obvious big question is, okay, this is all great. How do you actually make these changes? Or how do you make a machine learn all these things? I mean, as a human, I can explain all these things because I know it, but how do you make the machine learn all that stuff? And that's where the self-attention concept comes in. Okay. Now, I'll just use the nomenclature here so that we can build on that. So what you want to do again is you want to take this S cross D. S is the number of words in the sequence, and then D is the number of dimensions, and you want to convert it into this attention modified embedded matrix where you modulate or change the values up or down. Okay. Now, how do you go from this matrix to that matrix? Well, we can throw in a weight matrix because in deep learning it's all about weight matrices, right? Throw in a weight matrix, which when multiplied with the original will give you this attention modified embedding matrix. Now, if the original is S cross D and you want to produce, of course, the same size S cross D, what should be the size of this weight matrix? It should be S cross S, because S cross S, when you multiply it with S cross D, will give you S cross D back. So you know already that the weight matrix that you want is S cross S, correct? So let's say, again, this is a nomenclature. This original one you call as X, and what you want to produce is called as Y. Both of them are S cross Ds. And the weight matrix you want to call as W, which is an S cross S matrix. Okay. So the goal here is self-attention is a technique to come up with this weight matrix so that when you multiply it with this matrix, you get that matrix. Now, how do you compute this? Okay. Let's just look at the formula for that. I mean, the way you compute individual values here is Y11 as the dot product between W1, X1, 11 plus W12 x21, w13 cross x31 and so on, right? You multiply the rows and this weight matrix with the columns here and you would get this y, correct? Everything else remains the same and every cell is computed the same. Y35 is calculated as this row, the third row with the fifth column, right? If you look at Y86, you'd see the eighth row is multiplied with the sixth column and so on. But there's a very interesting pattern here that we should inspect that will give us an intuition as to why certain mathematical functions are performed in the self-attention formula. So let's look at this cell y11, and as I said, it's multiplying w11 with x11, adding that with w12 multiplied by x21, and you add that up and so on. So this row multiplied with this column, right? Let's say the values for w11, and of course this is what we have to train the neural network to do, right? You want to make these values. But let's say after it's trained and you have the right values, let's say W11 is 0.2, W12 is 0.01, W13 is 0.13 and so on, right? These are the numbers. Let's assume that we treat them as percentages, okay? Let's assume that. Why we make them percentages, we'll see that shortly. But let's say they are percentages. Then what does it mean? What it means is that you calculate this value here, y11, for this word, you're taking 20% of x11, 1% of x21, 13% of x31, and so on. Let's kind of double click on this. So what you're saying is, I have this original matrix, right, for all these words and these are dimensions, and they are x1, x2, x3, and so on. Okay. To calculate the modified context aware thing, I want to change the feature value for dimension 1 for the first word in such a way that I take 20% of that value of the same dimension from the first word, 1% of the value for the same feature from the second word, 13% of this for the same feature from the third word, 43% of the same feature from the fourth word, and so on. So what you're saying is I've figured out a way in which I can build the value of this feature dimension for the context embedding for that token by taking certain percentage of values from that same dimension from all the words, including itself, from that sequence. Correct? That is key. So when you add up all of these things, it makes 100%. You're distributing your feature values that you extract from all other words for that feature, right? Using this probability distribution where all of those percentages add up to 100. So that 20% of these features dimension 1 I'll take, 1% of this features, same features from word 2 I'll take, 13% I'll take from the third word, and so on. And every single cell here actually follows the same thing. Okay. And that's the goal. I mean, you want to come up with this weight matrix so that you can treat this as percentages that you're borrowing. Okay. Obviously, the question is how do you come up with that? Correct? But this is the key thing. That's why I'm double clicking on this. This is key. This weight matrix that you arrive at as long as you can design it in such a way that a neural network will learn so that all these rows individually add up to 100%, then you can mimic this thing, right? Where each dimension now, each calculation here will be, I'm borrowing certain percentage of that feature dimension from all the words to make up this context aware matrix, right? That is very, very key. And I'll tell you how to get to this thing, but that's the key. The feature of this particular matrix is this. And obviously, when you take this percentage thing, the one of the benefit is that it has this dimensional consistency preservation, which means that for the same token, you're saying that across all the dimensions you add up to 100%. So there's certain values of the same dimension that you're pulling from all the other words. So that's a nice property that you want to have. Okay. Now the goal is that you have to invent a technique that you can build this, through which you can build this matrix. Okay. Now let's dive into actually how you do that. Now the paper itself shows that it's on page 4. It shows that, okay, there is this formula that you can apply. This is the graphical representation of that formula, and this is the mathematical representation. Now most tutorials out there or videos out there show you this, and I think they use a language like, okay, by the way, QKV is query, key, and value, and they use words like query and the keys. They'll figure out how each word is attending to the other word and all that. There is no intuitive way in which you know why is it that you're doing this, why are you multiplying q times k transposed, and why are you dividing it by this and all that, and why are you doing a softmax. So I wanted to take a different approach and explain this thing. Okay, I want to do a step by step, and so very clearly why this formula works and why this formula is designed the way it is. Okay, you don't have to memorize anything. You will be able to intuit through this. Okay, so the goal is what? The goal is you take this word embedding matrix, positional embedding matrix, you add them up, you get this x, and the goal is to produce this context aware enhanced embedding matrix, the x attention. Okay, same size, x cross d and s cross d here. Now the way you do that is, by the way, this is a formula, and I implemented this using NumPy. That x is what? The word embeddings for all these tokens for a certain number of dimensions. Let's say the dimension is 7 plus the positional encoding matrix. Okay, the first thing you do is that, and you have to learn it. So the way you learn it is by throwing some weight matrices. You use 3 matrices, which we'll call as WQ, WK, and WV. And the size of each of these matrices, D cross D. D is what? The number of dimensions, the 7 cross 7, because here we're using 7 dimensions. Now you use these 3 matrices to make a copy of X. Okay, think about this. So you're just making a copy of X. The first copy you call as query. And you make that copy by how? You take this WQ and X and you multiply them together. You do a dot product. Okay, and that produces the same S cross D. Then you make another copy, which you call as key. And you do that how? You take X and you multiply it with WK, which is this matrix, and you make that copy. And you make a third copy called value. Same thing. You take X and you multiply it with this weight matrix WV, and you make this value copy. Okay, so QKV, query, key, and value. I'll explain why you're making copies and why you're not just taking X as is. Okay, you're making a copy first. Now the first goal here is what? The first goal here is to understand, how is each of these words, I walked into Apple Store, how is each of these words related to every other word? Okay, so the first thing that you want to do is that you want to intersect and take a similarity measure between the words in the same sentence, right? I walked into Apple Store eating an apple, and I walked into Apple. I want to do a similarity measure. And a similarity measure you can do by doing a dot product, which is like you're trying to determine the cosine similarity, right? So you take this matrix and you do this cosine similarity with this matrix, correct? So if you're doing a matching and you're trying to figure out how is this word related to the other word is what you're trying to learn. And that produces what we call as an attention score matrix. Okay, what is the size of the attention score matrix? It's pretty simple. Actually, let me show you here. Okay, so you're creating this attention score matrix. Okay, now let's dig a little deeper into how this is created. Okay, the first thing you do is, I said, you're going to create two copies. Actually, you make 3 copies. So we are only focused at this step on the query copy and the key copy. The query copy is what? Let's say you call it I walked into Apple Store, S cross D, and these are the different dimensions, Q1, Q. Let's say I denote it this way, and it is nothing but the X multiplied with this learnable WQ matrix and so on. Key is this. Now you are trying to find out how is I walked into Apple Store? Each word is related to each other. Clearly, you cannot do a dot product between S cross D and S cross D because you want to do a cross of these things. The way you do that is you transpose this. You transpose it. So the columns and the rows get transposed. Now I have a way I can say I, how is it related to I walked into Apple Store and so on. Walked, how is it related to I walked into and so on. So I can do that, right? Now I can take a dot product between these two. Okay. Now, when I take a dot product between these two, I get what? An S cross S matrix. S cross dot product of D cross S will give you an S cross S matrix. Correct? That's what I'm going to get. Now I have a matrix that tells you how similar is each word, right, to the other. Now, obviously, WQ, WK, and WV are all randomly initialized, it's random weights. So at the starting point of the training, it could all be random. There's no similarity. But you have to figure out a way in which you can train so that you can nudge the weights in such a way that you would be able to figure out the similarity. We'll see how we do that later. But here the idea is that by just taking q times q, the dot product q with the transpose of key, I'll be able to figure out the similarity between each word to the other words in this thing. That's why I create this S cross S, which you call the attention scores. It's just scoring the similarity between each word with all the words in the input sentence. Okay, that's why you get this S cross S matrix. Now each one S11 is what? You take Q11 and you multiply it with K11, add that with Q12, add that with K12 and all that. What does it mean? For this dimension 1, right? How is the word I and I related? For this dimension, let's say 2, which is Q12, how is I related to this dimension here for I, and so on. You do for the same word as well as for all the other words. So this is what you get. Now there's an interesting property that you see here. The property that you see here is if the, and you see the Q11, K11 plus Q12, K12 and so on till Q17, K17. 7 is what? The number of dimensions. Typically, you would have a lot more dimensions. You would have thousands of dimensions. It's a typical large language model in production has thousands of dimensions. So what it means is that if you actually choose a certain dimension size, those are the number of features, and you say it's in thousands, so that this number, actually the magnitude of this number is scaling based on the size of your dimension, which is not good because you really don't want to have very large numbers in neural networks. So what you do want to do is that you want to normalize that. The way you normalize it is that the standard deviation of the sum of these things converges to square root of the total number of dimensions, right? This is a mathematical property. I can go and reference that back later. That's why you see that in the formula here, what you do is that when you take the q times, you do a dot product between q and transpose of k, you divide it by the square root of the number of dimensions. So now you can actually normalize it so that the value, the sum of all these things doesn't get very big. You normalize that, right? That's why what you do is that you create from this attention scores, you create a scaled attention score, and you do that by just taking the raw attention scores and dividing it by the square root of the number of dimensions. Okay, you get this. You got your S cross S matrix. That's great. But what I told you earlier is this S cross S matrix should be, all of these rows should be percentages. So that what I get is that I get this percentage of this dimension from the first word, this percentage of the same dimension from the second word, this percentage of the same dimension from the third word, and so on. So you want to convert this into percentages. The way you do that is you softmax this. When you softmax it, around this axis, you say that each of these things now becomes percentages, correct? Now you got your attention weights. This is the weight matrix that I showed you earlier. That's the reason why this formula has a softmax. Now what you do is that you take this weight matrix and then you multiply it with the third copy that you made. What is the third copy? The third copy is called as a value matrix, right? Which is nothing but you put a trainable weight matrix here, WV, which is D cross D, and use that to make a copy of X, and you get this, and you multiply with that. And when you multiply with that, you have you're blended in all these other values into this each of these words, and then you get your context aware embedding matrix for this sentence, right? So that is the reason why this formula is structured this way. The key goal here is, the first step is I want to find out how each word is related to every other word in the same sentence. But I want to take that score, I want to scale it so that the values do not explode when the dimension value is very high. So I want to scale it. But I want to convert it into percentages. So I can say I want to draw this kind of percentage values from each dimension for all the other words. That's the reason why you softmax it and then you multiply to this value. So one question that immediately comes to mind is, why make a copy of X and to query, key and value three different matrices? Why don't we just use X as is? The reason we actually make a copy using these learnable weight matrices WQ, WK and WV is, if you see, what is the first thing that you're doing here? You're essentially trying to find out how similar is each word to every other word in the same sentence, correct? Now, if you were to take X as is and you were to do a dot product with X itself, yes, you'll know that I is very much related to I, walked is very much related to walked, into is very much related to into, apple is very much related to apple. So you'll get that. It's great. But what you want actually is to learn that in this particular sentence, you really want to change and nudge certain feature dimensions, certain features up or down based on what that word actually means in the context in which it appears. And the only way you can do that is to actually throw in some weight matrices so that you can essentially learn which one is more important, what feature is more important in the particular context in which the word appears, and so on. That is why you need to make a copy by using these trainable weight matrices. And once you train the transformer neural network, and I'll tell you later as to how you train it, you will know that it kind of nudges the weights in such a way that if you were to present it a sentence like I walked into Apple Store eating an apple in the future, once it's fully trained, it would actually index more on the brand and the company and the place for the first occurrence of the word apple, and it will index more on the fruit and the taste and all that on the second word occurrence of the word apple, right? That is the reason why you need to actually make a copy using these WQ, WK, and WV trainable matrices. All right. Now, if you look at it, this is how you can map it back to what is there in the paper on page 4. You make 3 copies: query copy, key copy, V copy, which is the value copy, and you do a matrix multiplication of Q times the transpose of key. Then you scale it, which is dividing it by the square root of the dimensions. There is this optional thing called masking, which is not used in the encoder-only transformer. It's used in the decoder as well as the encoder-decoder. We'll talk about that in other episodes. But you have the scaling. Once you do the scale, you have to softmax it so that you can convert each row into a percentage. And then you multiply that with the value copy, and then you get this. So that's what it is. So I think this is the most intuitive explanation of how this formula is designed and what actually this formula does. So now we know what self-attention is. Basically, you take in the embedding matrix, which has the word embeddings plus the positional encoding, and the self-attention converts that into a contextual aware embedding matrix. Now, if you look back at the picture, the transformer architecture picture in the paper, this block actually says multi-head attention. It does not say self-attention. So what is multi-head attention? So let's look into that next, which is at this layer of the transformer architecture. So this is again a single head attention. So let's assume that your context length, or S, is 4000, which means that this neural network is designed so that it can take up to a maximum of 4000 tokens at any given point in time. Okay, number of rows is 4000 S, and it has a dimension, embedding dimensions D of 1000, which means that the total number of columns and the total number of features for each of the words is 1000. Okay, and in a single head attention, you make these copies of query, key, and V of X, and you do that via the WQ, WK, and WV matrices, right, which are the trainable weight matrices. And we know, like we studied in the self-attention section, each of these WQ, WK, and WV are dimensioned as D cross D. Now, if D is 1000, the total number of parameters in each of these matrices is a million, because 1000 times 1000, D across D, is a million. Now, you have in this self-attention module here a total of 3 times a million, or 3 million total parameters, trainable parameters. So this is single head attention. So what you do in multi-head attention is you basically take the same X, right? And then you slice this matrix in the by the total number of dimensions. So what you are doing here is, let's assume that, just as a picture, so we have, let's say, 6 total dimensions. Okay, not 1000, just so that I can draw it out easily. So let's say it has 6 dimensions. Now what you do is that the first 2 dimensions, you would basically pass it along to the self-attention module. Okay, the next 2 dimensions you'll pass to another self-attention module, and the next 2, total we said 6, so next 2 you'll pass to another self-attention module. So each of this self-attention module is called as the head. Okay, so in this case, in this picture, you have 6 total dimensions. D is capital D is 6. You're slicing it into 2 dimensions per head, right, per module, self-attention module. So this is lowercase d, let us say. So each of these 2 goes to individual self-attention modules. So there are 3 heads here. So in this case here, if you go back to this table here, if your total number of dimensions capital D is 1000, and let's say you want to slice it across 50 different heads, each head, which is each self-attention module, will see only 20 dimensions. Then the first one will see 20, the next one will see the 20 after that, 10 dimensions after that, and the third one will see the 20 dimensions after that, and so on. So that is what multi-head attention is. Okay. Now, even in this multi-head attention, if you look at it, Yes, you do have. Let's just actually go back to this picture here, right? So you do have 50 heads. If you take this table, 50 heads. Each of those heads is only seeing 20 dimensions at a time. So you're seeing a smaller sliver of the total dimensions. So each of these weight matrices is going to be what? D, capital D cross, smaller d, right? Dimensions per head. It's 20,000. So each of these weight matrix here is 20,000 weights versus each of the weight matrix in the single head attention is a million weights. Million weights versus 20,000 weights. So each module has what? 3 weights. So 3 times 20,000 is total of 60,000. So each head sees 320,000 size weight matrices. So each head sees how many? 60,000 weights. And you have how many heads? 50 heads. So 60,000 times 50 is 3 million. So net you would have the same number of training weights. That doesn't change. It just so happens that each head only sees a smaller portion of the dimensions or smaller portions of the weights. So that's what multi-head attention is. And by the way, once each head does its self-attention calculation, you concatenate that. Traditionally, you actually use another weight matrix here to do the concatenation, but I'm just avoiding that for simplicity here. So you concatenate all the values that are coming out from each of the individual self-attention heads, and you build the context aware embedding matrix here, right? Now, so one important question to ask is basically this: why are we slicing this by dimensions, right? Why are you not slicing it by the number of tokens? So, for example, if you have S tokens and you have, let's say, N heads, you basically say S divided by N. Those will be the number of slices I'm going to create. The reason you don't do that is because one of the things about self attention is you won't actually build the contextual awareness of each word and try to understand the relevance of that word with the rest of the words in the sentence, right? And when you divide the number of sentences into individual slices, each head will only be able to see a fewer number of the words that are there in the sentence. So they'll not be able to build out the relevance of that these words have to understand the words that are not seen by that head, and the other heads will also not be able to see the words that are there in the process by the other heads and so on, right? So you clearly cannot slice it by the S dimension. You want to basically take all the words. So each head should be able to see all the words, but they just see a sliver of the dimensions. That's the reason why you slice them by the total number of dimensions and not by the total number of tokens. So, what is the benefit of doing it this way? Instead of doing it using a single head attention, why do a multi head attention? And the actual secret to that, I would say, lies in this formula here. What is this formula? This formula is creating the scaled attention scores, right? So, the scaled attention scores here, as you see, take the similarity between the Q copy, the query copy, and the key copy of the input embedding matrix, and you divide it by the square root of the dimensions. In the first case, in single letter attention, if you have 1,000 dimensions, you divide it by the square root of 1,000. In the second case, the total number of dimensions per head is 20. You divide it by the square root of 20. Okay. So with this background, let's actually now see what is the benefit in doing something like this. But prior to that, just to kind of give you a glimpse of what a real life production transformer looks like and how many dimensions it has. If you look at the original paper, attention is all you need. They said that the context length is 512, which means the total number of rows or the total number of tokens that they can see simultaneously is 512. And it has 512 different dimensions. But if you look at GPT-3, it said it can simultaneously see about 2000 tokens at a time, and the dimensions is 12,288 dimensions per token, right? And they said they would use 96 heads so that each head will only see about 128. Now we come to GPT-4, which is the most recent version of GPT. They can see simultaneously about 128,000 tokens, and each token has 16,384 dimensions. And they said they're going to have 128 heads, and each head still sees about 128 dimensions per head. Now, one of the common things I've seen being repeated again and again in multiple tutorials online is the reason why you have so many heads is because the transformer can learn more nuances from the text. And examples I've seen is think about each head as a linguist, and one linguist or one head is focusing on the verbs, the other one is focusing on the nouns, the other head is focusing on the adjectives, and so on. And as a result, they'll be able to see things better. Somehow that doesn't make sense. This is also demonstrated in another paper called Multi-Head or Single Head, an empirical comparison for transformer training by Liu, that kind of understanding, nuanced understanding of the language happens in other parts of the transformer. For example, the feed forward layer, or you would have the stacking layers and so on. and more recently things like the mixture of experts and whatnot. So I think that's a primary reason, and you cannot really rationalize that as a primary reason either. I think that's a secondary reason, secondary benefit that you get. There's a primary reason why you want to split it across multiple heads is speed and efficiency. So let me elaborate that on a little bit. So first of all, that paper showed that you would get 2 to 4x better performance when you use multi-head versus single head. Everybody understands that. That's the reason why you have multi-head used pervasively across all production transformer modules. So the first thing, as I said, is the division, which provides numerical stability. So let me just go back a little bit and let's use this picture to understand this. So we know that this picture we are dividing by a large number in single head and a small number in the multi-head case, correct? In the GPT-4 case, this would be square root of 16,000 in the single head. In the multi-head, it will be square root of 128. Now, what happens is that the Q and K matrices are made up of small numbers, fractional floating point numbers. When you multiply them, that becomes much smaller. But when you take that small number and you divide it by a large number, it becomes even more smaller anyways. So you start to lose some precision if the denominator is large, right? Now, let's go back to this slide. So what happens is that the multi-head, because it is doing, let's say, square root of 128, which is much smaller, you would see that you would have more precision of those individual values preserved in those matrices. And each head is actually working with higher precision numbers. So that is the first benefit. So first of all, you get numerical stability because you're preserving more of the value of those individual numbers. That's the first thing. The second thing is, if you again go back to this picture here, you see that if you look at the single head attention, let's say even if you have just 1,000 dimensions, you would have a million different weight parameters per matrix, correct? And you have 3 such matrices. Now, all these million per weight matrix are coupled together. What I mean by coupled together is means that in order to move the weights or nudge the weights in the right direction so that they are producing the right values, so that when you do the self-attention calculation, you'll be able to focus correctly on the right words based on the relevance that they provide in the context in which they appear. And when you do the back propagation to adjust all these weights, all these million weights are coupled together. You make a change to one, you have to make another change to the other, you have to make another change to the other. So there's a lot of parameter coupling that's happening here. A very large matrix is being coupled. But if you look at this, the multi-head case, there's a parameter coupling that's happening across just 20,000 parameters, right? So if you go back now to this slide here, what you're getting is that your convergence, when you start adjusting all these weights through back propagation and all, that happens much faster when you have a smaller size matrix to work with. Right now, that is key here, and that's one of the reasons why you see this like 2 to 4x speed up that you get when you use multi-head attention, because there is smaller size matrices that you, and which means less parameter coupling, and as a result, the convergence of the loss going down to zero happens faster. That's where you get the benefit. The second benefit of obviously also is the smaller size matrices will actually fit into the GPU's memory. I mean, just think about GPT-4. You would have a 16,384 times 16,384 size matrix that has to actually fit into 3 such matrices have to fit into the GPU memory. Versus if you take just 128 times 128 times 3, I mean, these are significantly smaller size matrices. So you also get this efficiency because the matrices can actually fit into the GPU. So that's the primary reason why multi-head attention is actually used in a transformer. It just so happens that because you have a fewer number of dimensions being looked at per head, you might be able to extract a little bit more nuanced understanding of what those features are and how are they related to each other across different tokens and all that. That's a side benefit. It's not the primary benefit. Okay. Now, before we start digging further into the transformer architecture, I just want us to bring it back to seeing what benefits we have seen in processing text using a transformer just from the concepts that we have learned so far, the self-attention and the positional encoding and so on, compared to how we did natural language processing in the past using recurrent neural networks or LSTMs. So if you take a sentence like this, I walked into Apple store eating an apple. Before the transformers, when you use a RNN or an LSTM, you would process one token at a time. And when you're processing one token at a time, what you're doing is that you process the first token. You start with an initial context and you process it to the first token. The context is updated. Then you process the second token. And you also pass the context that you have updated in the prior token to this one, which further updates that context and passes it to the next one. And you do that. So if you have n tokens, you are making n such independent calculations. And you pass the context one after another to the one token to the other. This is what we did, right? It is slow, it is not parallelizable, and tokens are just looking at the prior tokens that appear before it to build up the context. What the transformer has allowed us to do is not just see tokens one at a time, you see everything at a time. Why do you see everything at a time? You take the embedding matrix and you add to it the positional encoding. So that gives you both the positional awareness of the token as well as its feature dimensions through the embedding matrix, and the self-attention or the multi-head self-attention. What it does is that it builds these relationships and it tells you how you move the individual dimension, feature dimensions values up or down based on the relevance that each word offers to understand the context of that word in that sentence, correct? So what the transformer does, if you think about it, it looks like this. It's a mesh, right? Each word can see every other word parallelly, and each word is trying to understand how it is relevant to the other words in that same sentence or the same context, and how other words are relevant to itself. Each word simultaneously can figure that out, right? Now, this is a very big leap, because without something like this, you would never be able to see the kind of commercial applications that we see with things like ChatGPT and so on now. Because, I mean, ideally, you start using ChatGPT today by giving, maybe start off with a few prompt words, but over time, you start building more and more into the context window, and you would have 1,000, 2,000. Sometimes you might throw an entire PDF file and say, I want you to summarize this for me. So you have thousands, tens and thousands of such words. You would never be able to get the performance, latency, and all that with the recurrent neural network. You get that with transformers. So it's a speed benefit. You also get this benefit that in an RNN and an LSTM, you would take the word embeddings as is, and you're really not morphing or changing them based on how they appear in the sentence. So the apple here, the first apple occurrence of apple and the second occurrence of apple in an LSTM or RNN would carry the same embedding matrix. However, in the case of a transformer, the second apple will directionally move more towards the fruit, and the first one will move more towards the company. So that's the second benefit that you get. So you get better understanding of language to the transformers. Okay. Now let's go to the next part of our transformer neural network architecture. So I'm going to talk about feed-forward network. I'm going to skip this layer called add and norm. I'm going to come back to this after I talk about feed-forward layer. Okay. What is a feed-forward network? Why do you need it? So let's take this sentence. I walked into Apple store eating an apple. Okay. Now let's look at another sentence. I entered an Apple store chomping on an apple. I'll give you another sentence. Taking a bite out of an apple, I stepped into an Apple store. Now, to a human, we know that all these three sentences more or less mean the same thing. Phrases like walked into, entered a, stepped into, more or less they convey the same meaning. Now, how do you make the machine learn that? Yes, self-attention tells you that you need to weigh the first apple more towards the company, second apple more towards the fruit, and it also tells you that you need to nudge the dimensional feature values of each of those words and whatnot. But you actually also want to teach the transformer that things like this could actually mean the same thing. The way you do that is you need to figure out how you can throw in more weights into it, and you need to train those weights so that you learn that information, right? So the way you would do that is you take the context aware embedding that comes out of the multi-head attention and you project that into a larger space. Okay. So an analogy would be, okay, you have this matrix and then you take a magnifying glass and then you look at it and you zoom in 4 times. And when you zoom in 4 times, again, it's an analogy. It's not a mathematically correct way of looking at it, but it's an analogy. You'd zoom in 4 times and then you would be able to look at more nuances that are exhibited by each of these features across all these words. Correct? Now, how do you do that using math? The way you do that is you would create a feed forward network that allows you to project these dimensions from D to 4 times D. So you're doing a 4 times magnification. Now, why 4 times? Why not 8 times? Why not 3 times? Why not 10 times? Why not 100 times? Actually, it can be anything. Empirically, what they've observed is that doing it 4 times actually yields good results. Sometimes just overdoing it does not give you much benefit. Remember that the more you add, the more memory consumption is there, more computations are done. So it actually slows things down. It consumes more resources. So you have to strike the right balance between just adding more versus getting good quality results, right? Empirically, they found out that actually projecting it to 4 times is good enough. So what they do is that they project it to 4 times. Now you have D dimensions being looked at by 4D number of neurons. I think one way of looking at it is that. Right now, once they look at it, then you want to project it back because at the end of the day, you still have to work with the same S cross D matrix, right? So, but you just need to build in more weights that can, when you throw in words like I entered, I walked into, I stepped into, and all that, it will nudge the meaning in the similar direction. That happens by these weights here. Okay. So, how do you take this 4D that expanded projection and project it down back into D, you create another layer in the feed-forward network, which is size as D. So to cut a long story short, you throw in two weight matrices. The first weight matrix is in the first layer of the feed-forward network, which is sized as D, which is total number of rows, times 4D, total number of columns. So D times 4D. So if you take S cross D, which is the X attention that's coming in, and you multiply it with D slash 4D, what you get is S cross 4D. Okay, now you have a total number of tokens and 4 times its expansion, right, on the dimension space. And then you project it back using 4D times D and you get the S cross D back again. That's all there is to this. That's all the feed-forward neural network does. And this one allows the neural network to learn more because it has so many more weights that it can train, so that when you train it, I mean, I've actually not told you how to train this yet. We will see that in the next episode. But when you train this, and if your training objective can be designed in such a way that you say, I walked into Apple store eating an apple is similar to I entered an Apple store chomping on an apple is similar to stepping into an Apple store, I was eating an apple or something like that. All of them are meaning the same thing. These weights in the feed forward neural network will adjust themselves in such a way that you would extract the fact that they all more or less mean the same thing. Okay, that's what a forward neural network does. Now let's look at the next one. Now let's come back. I told you I jumped the add and norm and I went to the feed forward. Now let's just come back. The reason I did that is because I wanted to give you a continuity of nuanced understanding of language that happens first at the multi-head attention and then the feed forward. I want to come back to the mechanics of optimization by going to the add and norm. So let's look at norm, which is layer normalization. So an intuitive way, an analogy to understand layer normalization is think about layer normalization as a sound engineer for the transformer. So what does it mean? So we know that the multi-head attention helps the transformer figure out how words are related to each other. We got that, correct? However, what happens if, let's say, some of the feature dimensions values are much larger for a given word than the values of other features of the same word? That is critical, of the same word, right? As an example, let's say dimension 2, right, of this token is 100 and dimension 3 of the same token is 4. Does it mean that dimension 2 is 25 times more important than dimension 3? It might not. So that's a problem. So it's almost like the saying that goes, the loudest person in the room should not be the one who always wins. Similar to that, the loudest feature should not be the one that will dominate the calculation. So what you really need is a technique by which you can normalize all these signal strengths of all the features of the same word, multiple features, so that no one feature will dominate the others. And similarly, no one feature gets muted or lost out because it's carrying a lower signal strength at the beginning. Now, the way to do that is using normalization. I actually touched upon normalization in season 1 exhaustively. I talked about input normalization. I talked about batch normalization. So in transformers, you use layer normalization. And layer normalization means the following. You take a token across all its dimensions, you normalize it. Okay. Go to the next token across all the dimensions of that next token, you normalize it. Okay. So that is what you do with layer normalization. And if you just look at the original plot here. So let's say that these are the values as an example for a sentence that has 9 tokens and it has 4 dimensions. And these are the 4 dimensions and feature dimensions. And let's say I want to plot, let's say this blue line, right? For token, blue line is token 1. Okay. Then you say, okay, the value is 4 or dimension 1, feature dimension 1. For the same blue line here, for the second dimension, dimension 2, it is 2. And the next one is 0. And then it goes to 3 and all that. So the average is 3. So I'll do a dotted line and show 3 here. For the next token, which I'm showing in orange, the first value is 0, so it starts 0 for feature 1. For feature 2, dimension 2, it's 3, so it goes up here. For feature 3, it's 2, it comes down here. And feature 4, it goes to 4, it goes there. And its average is dotted line here. The averages are not overlapping, so everybody is not normalized. One way of looking at it, right? What normalization does is that it normalizes the value so that the mean of all the features for a token comes down to 0 and its variance comes down to 1. So when you do something like that, the formula is extremely simple, by the way, right? And it's, by the way, done token by tokens across all features of the token. You calculate the mean and you calculate the standard deviation, and then you take individual features, subtract it by its mean and divide it by standard deviation. So when you do that, the same distribution of the values of the features is retained, but you see that the mean is zero. So everything is centered around that. Now, this gives you stability in training. You don't have this loud feature values overwhelming the calculation, neither do you have lower feature dimensions getting muted out. Okay, that's why you have layer normalization. All right, now let's look at residual connections. So residual connection is actually a pretty straightforward concept. What it says is, okay, so when you let's try to understand the concept of residual connections first, right? Before we apply it to transformers. Residual connection says that, okay, when you are processing a input and you're sending it through multiple blocks or multiple layers or however the neural network is designed, and each block is modifying the signal that is coming in from the previous layer. After a certain point, you will see that because each block is modifying the input signal that's coming from the previous layers, you will see that important information that might be relevant for some block in the future is not available for it because it got muted out as it's going through these different layers. So the idea behind these ResNet or residual connections is saying that, okay, you propagate the signal through all these modules, but you also send along with that signal from the past, right, to the future module. Like for example, here, let's say this block is getting the signal from the previous block, X4, but it also wants to see what happened two blocks before that, X2. So you send both these signals and then you have both the modified signal as well as the original signal. So this block does not just operate on what is modified, but it also has a reference to what was original or what was there before the modifications happened. And if it feels that it is relevant, it can actually act upon that, right? That's all residual networks is. And by the way, the reason why it is important is we are talking about small floating point numbers that get modified as you're going through these networks. And when small numbers get modified, you start to lose certain important information which you can preserve when you have a residual connection. So that's a general idea behind residual, or sometimes they're also called skip connections. So how is it relevant to the transformer? So the transformer, what happens is that you take, for example, there are two residual connections in the encoder block, right? The first one is the addition of the original word embedding enhanced with the positional encoding, which is the X, which you feed to the multi-head attention, which converts that into a context aware embedding matrix. What you want to do is that before you pass that forward to the feed forward network, you want to pass that context aware embedding, plus you also want to pass the original, because the feed forward network wants to see everything, so that in case the multi-head attention inadvertently, because initial weights were all random, muted out certain important features, maybe the feed forward network can catch that, right? So that's the general idea behind having residual networks. And the same thing happens even after pass it from this modified thing. You again skip forward from the feed forward to the next layer and so on. Okay, so now we have understood that. Now let's look at the next part, which is stacking. So in the transformer neural network architecture in the paper, it is shown in this block, and then it says NX, which means there are n such blocks in the neural network architecture. So what is this thing? Why do you need it? Let's understand that next. So language is a complicated thing. And before we look at how machines try to understand language, let's actually try to understand how humans understand language and how our understanding of the same text changes over time as we are exposed to more and more and more such sentences. Let me explain that using an example. So let's say there's a quote like this: "Man looks in the abyss. There's nothing staring back at him. At that moment, man finds his character, and that is what keeps him out of the abyss." Now, this is one of my favorite quotes. It's very profound. It's from the movie Wall Street. But if you were to give the sentence to, let's say, a middle schooler, the way the middle schooler will understand this is he'll look at it and say, "Man looks into the abyss." He'll take a literal meaning. Man is looking into some valley. There's nothing staring back at him. So he'll say, "Oh, maybe there's no other human in the bottom of the valley. Nobody's looking back at him." Then read the next sentence. "At that moment, man finds his character." They'll say, what does it even mean? To a middle schooler, what does it mean, right? That, okay, nobody's looking back from down the valley to me. What does it mean that I'm finding my character? And then it goes into, and that is what keeps him out of the abyss. Then this one doesn't mean anything either. What does it mean that why would nobody looking back at me from the bottom of the valley mean that I will not fall into the valley? That could be the literal meaning that a middle schooler can extract from the sentence. Now, you give the same sentence to somebody who has lived, experienced life, and seen a lot more text and whatnot, right? Let's say you give it to somebody who is in there after their undergrad. Now, to them, they look at this and say, "Man, this is quite philosophical." They don't look at it literally. They actually try to understand the nuances that are there in this phraseology, right? And how do they do that? The reason they have built that is because they have seen a lot of text from their middle school till their end of undergrad, and in all that text they have been able to understand that you don't have to take everything literally. You have to understand some nuances of what is really being said, right? And they build that by getting exposure to a lot of text, by getting exposure to different phraseology of words and all that, correct? Now you want to mimic this behavior of humans so that you can train the machine to do the same thing. And that's where stacking helps. So the idea behind stacking is actually very, very simple. So what stacking does is you take your transformer, you do the initial word embeddings plus positional encoding, you get that X. You pass it through an encoder block. An encoder block is nothing but it goes to the multi-head attention, it does a layer normalization, goes through a feed-forward network and all that. And out comes a context-aware embedding matrix. Now you pass that as an input to a different encoding block, which is actually designed the same, architected the same way, but it has its own set of weights. So the original first one got the X from adding the word embedding plus positional encoding, and it emitted out the X attention, right? Which is attention weighted this X. So you pass that X attention weighted X to the next encoder block, which has its own weights. Same architecture, has different weights. And that will further understand this meaning, and it will create another X attention prime, which you pass to another encoder block, which is architected the same, but it has its own set of weights, which emits in an X attention prime and so on, and you keep on stacking more and more encoder blocks, and which means more and more weight parameters, and then finally you get the contextual embeddings at the end. Right now, how many blocks? The original transformer paper said that if they use 6 blocks, which means that 6 encoder blocks they stacked one on top of the other, they got good results. Llama uses between 30 to 120 blocks. Why that variance? Because again, Llama has multiple model sizes, 7 billion, and they are much more bigger ones and all that. And for the smaller sized models, they use, which have fewer parameters, they use fewer number of blocks. For the very large models, they'll use more blocks. GPT-4, for example, uses between 100 to 120 blocks. DeepSeek uses between 30 to 80 blocks. There's no magical answer to how do you arrive at the number of blocks. Through empirical studies, you can figure out, and you strike the right balance between performance and quality when you're choosing the number of blocks. But the key concept here is just like a human, when they take the same text, process it once, again reread it, process it again, reread it again, and process it again, and all that, and they build better and better and better understanding. You can mimic that same behavior by just stacking multiple encoder blocks, one on top of another, and just pass the output of one as input to the other, and you would be able to make this transformer understand nuances of text. And in the end, what comes out is this contextual embedding. By the way, this NX is N encoder blocks that you have. By the way, when I talk about the decoder architecture, decoder also has this N decoder blocks. Now let's try to put everything together. I mean, I showed you the concepts. I gave you the intuition behind how these things work. I told you why the formula is for self-attention is designed the way it is. But now you've got to map it back to actual implementation, because you'll be able to understand and remember things better if you actually implement the transformer yourself. And what I've done here is to make it very simple and clean. I just use NumPy and I've implemented the encoder-only transformer here. So in the encoder-only transformer, let's start with the bottom line here. I pass in a string, a sentence. I walked into Apple store eating an apple. It goes to the encoder-only transformer. And I'm saying that I'm sizing my transformer with the maximum sentence size S, which you have seen in the matrix as 10. So 10 rows, 10 tokens. And each of those tokens have about 32 dimensions. And I'm also saying for my multi-head attention, I'm going to use 4 heads, which means what? Each head will see 32 divided by 4, 8 dimensions at a time. And I want to stack 6 such blocks together, one after another. So now let's look at this line here. So the word embedding is the first one. So word embedding, what do? You pass the input string. I walked into Apple store eating an apple. You tokenize it and you pad it so that you hit the maximum sequence length of 10. You get the word embeddings. That gives you the S cross D matrix, which is embeddings. Then you pass it through the positional encoding matrix, which is calculated this way. I showed you, right? The sine and cosine. So you get the positional encoding matrix, which is also sized as S cross D. Now you add both of them up. So this addition of word embedding plus positional embedding, word embedding plus positional embedding, that becomes your input X that you passed your transformer block. Now a transformer block is made up of multiple weights. It has made up of the WQ weight, so that you can make a copy of this X by multiplying X with this WQ matrix, make a copy called key with the WK and can make a copy called value with the WV value, right? Matrix. So WQ, WK, and WV are size D cross D. So you have D cross D. But however, I told you that I'm using not one self-attention module. I'm using four self-attention modules because four heads. See, each one only sees 8, right? So total is 32. Total number of heads is 4. So each head sees 8. So I'm doing times 8 each. That's what the size of each WQ, WK, and WV is. I also need to have feed forward neural network, which is going to have the D times 4D, right? And the first layer and 4D times D in the second layer, and I also have bias matrices. Feed forward neural network needs both weights and biases. So that this is one attention block. I am going to have 6 such blocks. Means 6 different weights plus biases. Now I'm going to process this. The first thing in processing is what? Processing the multi-head attention. So to that I pass X, which I got through this, right? And then I go in there for each head. I will make a copy of that, the query copy, the key copy, and the value copy, and that I will send it through. I'll calculate the attention scores by taking a similarity measure between the query copy and the key copy, which tells me that I walked into Apple store eating an apple. How relevant is I in understanding I itself walked into Apple store eating an apple? How relevant is the word walked to understanding I, the word itself, the word into, the word apple, the word store, and so on. So it's a S cross X, S cross matrix that you get out of doing this cross product to get the similarity. I also told you that you actually have to scale that by the square root of the dimensions, right? To keep that value correct. So you don't have the additive property that I told you can make this value very big. So you can scale it down by dividing it by the square root of the number of dimensions per head. Then you have to send it through this softmax layer because remember I told you that the attention weight matrix is an S cross S matrix where each row is a percentage of the same dimensions values that you take from every other token, including itself. So you need to make it a percentage. So each row has to have a percentage. So you do a softmax across this attention score matrix. So you get an attention weight matrix, which is softmax, which is giving you a probability distribution that adds up to 1 on a per row basis. And now you take that and you multiply with the value copy of this X. You do that for every head and then you concatenate it at the end and you get your attention weighted context aware matrix, embedding matrix, which you call X attention. That comes out from this layer here. So what comes out of the multi-head attention is this attention weighted context aware embedding. Now that you pass through layer normalization. But what do you pass? I said that you have to also pass the residual connection with the value that was there before as well as the modified value. The value that was there before is X. The modified value is X attention. So you sum that up and pass it to the layer normalization. And the layer normalization will ensure that it normalizes every feature value for a token so that the mean is 0 and the variance is 1. So that's what it does. And then you get the X norm back. Now you pass that to the feed forward neural network. The feed forward neural network does what? I told you it magnifies it into 4 times the dimension space and then it brings it down. That happens in the first layer and then it brings it down into again an S cross D matrix and it emits that out. So what goes in here is this really the X norm. What comes out here is the XFFN. Now you pass that through the add and norm again. That is, you have to pass again. There's a residual connection also here. So what came out here is X norm. What came out here is XFFN. You add that together, that's a residual connection, and you pass that through layer normalization again, and you get X out. Now you pass that out, and that becomes your context aware embedding matrix for this sentence. That's one block. Now you pass that through all the 6 blocks, right, one after another. So this whatever came out of the first block becomes the input to the second block, which has its own set of weights. Whatever output comes out of that goes to the third block as input and so on, which has again its own weights. How many blocks? In this particular implementation, I have 6 blocks. So this is your end-to-end implementation of the encoder using just NumPy. So now you have both an understanding of the theory, the actual intuition behind all the formulas. You actually know how to implement it. But a big question now remains. How do you actually train this thing? To train a neural network, throughout our episodes, I've been showing you that you have to have an input. You understood that the input is going to be the input string. But you also need to know the ground truth value so that you can compare your prediction, which is ypred, with the ground truth value that you give as training. So what is our y true and what is ypred? I understand that the x is the input sentence, but what is y true and what is ypred? And how do you measure the loss? How do I know that my prediction is off so that I can back propagate that loss to adjust all these weights? And what is the output function? What is it that I'm really trying to output from this? I understand that I'm outputting a contextual embeddings, but what is it used for? So these are actually important questions. And I'll cover all of this in the next episode, where I'm going to talk not just about taking this encoder architecture and telling you how to train it, but I'll also show you how do you fine tune it for different use cases like classification use case, similarity measurement use case, named entity recognition use case, and all that. And the way I have designed the next episode is not just focus on the concepts and the intuition behind those concepts, but I'm actually going to demonstrate that through practical applications. We'll build out some applications that will show you some of the most beautiful things that you can do with a encoder-only transformer, and some of the beautiful large language models that you can build just with the encoder. All right. Thank you very much for attending, and please subscribe to my channel and please share. And until next time, happy learning. Thank you.